we're very pleased to welcome Sydney Doe, who is in fact a Sydney Sider, as we call locals, having done his undergraduate degree at the University of Sydney, his other place here in Sydney. He's got his Masters and PhD from MIT. He's currently working at JPL in the Project Systems Engineering and Formulation section, and is working on Mars sample return. He's going to be talking about selecting sites for working on Mars. Sydney.
Thanks, Andrew. Really happy to be here, back in town. I left Australia 10 years ago, so it's great to come back and see everyone and see the growing excitement in space. Today I'm going to be talking about the considerations for selecting a landing site on Mars. We've heard a lot over the past half a day about this concept called exploration zones. I'm hoping to give you a quick background on that and how we're trying to study and characterize the constraints behind how one would go about selecting a landing site for human missions to Mars. So, we've been actually studying how to send humans to Mars for over 60 years. So, Rob mentioned last night, Werner von Braun's Dust Mars project. Back in the day, R.C. Clarke came up with some concepts. There was a lot of activity in the early 90s at the case for Mars workshops, which was run by university students. And then in 1988, a lot of activity began at NASA when Bush Sr. announced the Space Exploration Initiative. And periodically, NASA's come up with what's called design reference missions or architectures. A common trait across all of these is that there's never been a real detailed discussion about where on Mars, longitude, latitude, should we land and put our base. And so we're very much interested in that now, and the reason as to why is because it's become policy. And this really began in 2010, where it was declared that the long-term goal of human spaceflight for NASA will be to expand human presence beyond low Earth orbit. A few years later, the National Academies came out and said the horizon goal for human space exploration is Mars. That's our long-term goal, and that's consensus among the spacefaring nations of the world. How you get there is a question mark. In 2014, NASA kicked off what's called the Evolvable Mars Campaign, which is a series of studies looking at various trades of how you'll transport crew there, what your propellant combinations are. It started looking at what your landing site should look like and what you need on the surface. 2015, a document came out called Journey to Mars, and it outlined the strategy and policy guidelines that NASA was hoping to adopt to develop a sustainable human Mars exploration program. And then this was reaffirmed earlier this year in this year's Authorization Act, where achieving human exploration of Mars and beyond was the key objective of the space program, at least in the US. So we've done this before, we've selected landing sites before, we've had over 20 years of continuous exploration of the Martian system. Sojourner, Mars Pathfinder, landed on July 4, 1997, and we have a number of missions coming up. So here are the various locations on Mars we've landed. And when we do this, we typically define a landing ellipse and define scientific regions of interest by which we want to explore once we land there. So a little bit more details on how we select a landing site for at least our rover missions. It's primarily driven by how much scientific return you can get from that site. So typically you have scientists like Bob here proposing a site and specific regions of interest. And then there are engineering constraints that we take into account. So for example, landing safety, atmospheric characterization, what the winds are, what the altitude is, what the rock distribution is. You don't want to land on a rock. And your lighting, for example. And the survival of the rover. So what the season is at that landing site when we land, what the insulation is, what the likelihood of dust storms is. That affects how much solar power we get if we run a solar powered rover. And also the temperature, which is quite important for survival through the night as it drops to very cold levels. We're also interested in rover traversability. So what is the rock distribution, what are the slopes and the terrain type. We historically wanted to avoid sand dunes because we got stuck in them. With Curiosity, we're relaxing that constraint. We want to drive in softer materials so that we don't damage the wheels, as Bob mentioned. And you know, it's very difficult to navigate through a rock field like this, so we try to avoid things like that. So, what are the considerations for landing humans on Mars? So, we've really started focusing on this in about the 2015 period onwards. And so in early 2015, both the human exploration and the science exploration side of NASA, so the robotic and the human side, got together and started jointly beginning activities to focus on identifying the requirements on human landing site selection. 2015, some working groups were formed, and some of the people in this room were a part of those. So an ISRU and civil engineering working group was formed to identify how we could use local resources to support a human hub. And Rob discussed a lot of that last night. There was also a science team that was formed to discuss what are the scientific objectives of going to Mars, and this would feed into the selection of your landing site. In mid-2015, there was an open call for what is called an exploration zone, and you've seen a lot of references to that in the last two talks. Essentially, it's a 100-kilometer region that we perform exploration in. And then in October 2015, NASA held the first human landing site selection workshop, and that was basically the confluence of all of these the outcomes of these working groups. So the engineering constraints coming from those evolvable Mars campaign studies that I previously mentioned, the resource need and availability from that working group and the scientific objectives. So out of this, 47 exploration zone candidates were proposed. So some more details, 100-kilometer radius, you've seen this image many times. Latitude band between plus minus 50 degrees. That's driven by accessibility and thermal considerations. It contains a habitation site, so where you set up your hub, and the constraint is that we want to be somewhat close to our landing site locations, and we have to drive too far once the crew gets to the surface. Landing site has to be flat, low rockiness, so very similar to those robotic constraints, robotic Mars mission landing site constraints that I mentioned earlier. And then we're primarily interested in water, and also interested, but not as much as water, in other minor metal and silicon resources. And so ideally we wouldn't have to dig too deep to access this water, and it would be somewhat close to our power infrastructure. And the working estimate we've been working off of is it should have at least 100, it should have enough feedstock so that you can get 100 metric tons of water from that site. The science regions of interest were really categorized into astrobiology, atmospheric science, and geoscience. So to give you a physical intuition for what an exploration zone kind of looks like, there's this diagram here, but just in terms of scale, this is what it looks like. So this is the difficulty between robotic exploration and human exploration. So the exploration zone is 200 times larger than any ellipse we've ever had for robotic missions. And these are the length scales of some of our rovers. You can see the traverse distances if we're going out to different science regions of interest. They're a lot further than what is taking MER, for example, 14 years to cover. So we're going to have to drive a lot faster over longer distances if we want to do a decent amount of exploration. So these are the 47 exploration zone candidates that came out of that workshop. They range across the latitude bands. Each of the proposals has a very strong idea as to why their site is the best. There are various camps ranging from, we should go to where we've already been to we should go to new locations. There's also the question of what that water feedstock we want to focus on is. Is it going to be in the form of hydrated minerals or subsurface ice, which then has implications in the mining systems that you develop to extract these resources. And that conundrum is kind of what we've really been focusing on since this workshop. So I want to quickly briefly talk about the trade space, the various considerations that we need to understand when we think about selecting an exploration zone, which contains a landing site and those other regions of interest. So you saw this diagram earlier. This is a very simplistic representation of the different drivers of this decision. Our science objectives are distributed into these three subfields, and obviously they can be further and further decomposed. Engineering constraints, heavily driven by your system architecture, so there's back and forth cross-dependency here. So this entails what your habitat looks like, what your power source is, your accessibility, so your landing system and then your ascent system. And these are those traditional landing site constraints that we think of for rover missions. On this side, the resource need and availability, very much a function of your system architecture. So what's your life support system look like? How many crew? How many spacewalks are you going to go on? Because every time you go on a spacewalk, you're using water as your coolant and you're basically sublimating it to the Martian atmosphere. And clearly driven by what's available at your site. Again, what form is that water in? Is it accessible? Is it extractable? What's its quality? How much do you actually have? And clearly this is driven by the science and how that was formed. So in this talk, I'm going to focus on what I think is of more interest to this community. Oh, also I'll note that it's interesting to note that here, anything that's in black text, the typically things we measure, white text, the things that we design and select. So we need to measure a lot of things even before we can start to design things at some level of fidelity. So right now we're really interested in taking more of these measurements and coming up with new creative ways to use our existing assets in orbit and on the surface to gather further insights into these particular things that we want to measure. So with respect to this community, and for this talk, let's just focus on this subset of decisions. And essentially, since the Human Landing Site workshop, we've been attempting to characterize these things that we measure. And we can basically split it up into the right side and then the left side. And I'll talk about this combination of decisions in the next couple of slides. So let's talk about this right side here. So how your resource need and availability affects your exploration zone location and how you take into account all these considerations. So following that workshop, two main things came out of it, well, several things, but I'll talk about two of them right now. There were requests for further data to be taken from our orbiters, mainly the Mars reconnaissance orbit around Mars, for basically spectral data and high-resolution visual imagery. And one outcome of that workshop is that we were able to identify 4 of the most common types of water resource deposits, and we were able to study them further. So this chart kind of summarizes what those are. We thought of many, and then some were crossed out due to other engineering constraints, so latitude bands, for example, and accessibility. Essentially can be divided into your mineral deposits and your water ice deposits. And so these, this table summarizes the activities that we've been undertaking since then. And so many of you have heard of the MWIP study, the Mars Water ISRU planning study. So that really focused on the mineral side, trying to characterize what that might look like on Mars, and having a first estimate of what the systems that are required to mine those materials would look like. Water mining on ice study covered the water side. I'll talk a little bit more about that later. And then we also recently sponsored a gypsum mining and processing study. So that happened earlier this year. And I'll talk about the logic across these, why we did these studies and when we did them later on. So the ones in red, essentially, the objectives are to define a reference reserve case for each of the different types of feedstocks and start to look at how you might process these. And the ones in blue are essentially you're processing existing data products and you're trying to get a better understanding of the current distribution of water in all its forms on Mars. And so I've just listed these up here. In the next couple of slides, I'll highlight whatever study that I'll be referring to so you can track what I'm talking about. So the MWIP study basically found that to go from where we are today, we have a fleet of spacecraft around Martian orbit, to having an understanding of what it takes to get water from Mars, we need to do exploration with our orbiters, and then through that the output would be an understanding of what the proven reserves are, and then you would develop the production system to extract useful water from those proven reserves. And so it comes in 2 phases, the exploration and the production phase, and these reserves are the key thing we need to understand. However, understanding what a usable reserve is requires both upstream and downstream knowledge. You need to understand what the production system is and what it's capable of mining, essentially, and then understanding the reserves itself. designing the production system itself requires understanding what's already there. So you have this coupled problem of you need to both design your ISRU system and at the same time, in parallel, improve the fidelity of your understanding of what's available and what's accessible. And so that's why we've basically looked at those two sides of that coin. So those were the red and the blue classes of studies that I showed in the previous slide. So the other thing that the ENWIP study found was that, at least on the minerals side of that trade versus hydrated minerals versus subsurface water, you have a common underlying ISRU architecture where you essentially heat up your feedstock, you condense your water out, you combine it with atmospheric CO2, do some processing, and boom, you have rocket propellant. It also found that gypsum was the most attractive feedstock out of those types of minerals that we looked at, due to its minimum energy requirement relative to the others. The study also went and looked at what other types of data we actually need to measure to characterize how the various types of feedstock exist on the Martian surface or subsurface. And so in this table, we ranked the importance of information from 1 to 3 for the different types of feedstocks that were examined. Blue are things that we think we can do, we think we can measure it or better constrain it from our satellites in orbit. And green are things that we think we need to put something on the surface, and touch Martian rock to measure. So moving on to the mining water ice study, did basically the same thing, and it really focused on a concept called the Rodriguez well, which has been used in Antarctica since the early 1960s, and attempted to characterize the energy demand as a function of the production rate, if you will. And so in this study, it was basically surface strip mining was essentially ruled out due to concerns with sublimation. The gypsum study, so as I mentioned earlier, ENWIP found that gypsum was the most attractive of the minerals types of feedstocks. However, there was an assumption there that the gypsum appeared in a granular format. And this study basically tried to understand what it would look like if it came in a more block form. So if you needed to invest energy into crushing your gypsum before calcining it and trying to extract water from it. And so there were two components to this. We studied how gypsum is processed on Earth and tried to use that to inspire what a gypsum mining system on Mars might look like. So these are some images from a mine in Michigan. And then we also did an analytical study to try and understand what the optimal grain sizes are for the most energy efficient heating. So that's led to some forward work. I'm going to skip through, or I'm going to move faster. Since then, we've had 2 activities which are co-located, and essentially we're attempting to create better maps of the water distribution on Mars, both in the form of subsurface ice and hydrated minerals. And so the current status of this, we've received the proposals from the Mars science community, and we're going to make our selections very soon, and actual maps they're expected in October 2018. So I spoke about the right side of this trade space, if you will. I want to quickly talk about the left side. And so these are the engineering constraints. I want to talk about 2 things that I think are very much applicable to this community. So one of the tools that we've been able to develop for the Mars 2020 rover is essentially Google Maps of Mars. So we can say if we land at this particular point, or up here, and we have various regions of interest that we want to go to, because we've mapped the entire landing ellipse in terms of its terrain, its rockiness, and its slope data. We can generate these paths for each potential landing point. So landing is a stochastic phenomenon on Mars. You have a landing point cloud. If we do a Monte Carlo simulation of these paths to these regions of interest from all these landing points, you start to get a convergence of many routes into common paths. So essentially, we can define where the highways are on Mars, where we're going to have mass transportation of materials between different regions of interest in our processing sites. The other thing I want to mention is on the resource demand side, there have been studies that have looked at, how much water, oxygen, food, nitrogen, CO2 do you need for a habitat and the Mars Ascent vehicle that will return astronauts as a function of your life support system architecture. And so we can start to predict those and do cross-system trades beyond just the ISRU and other aspects of your system, and then feed that into what your ISRU system design might look like. So that is pretty much the end of my talk. The next steps we're doing, we're going to begin those Mars water map development very soon. We're in the early planning stages for the second Mars human landing site selection workshop, which is tentatively planned for midway through next year. And we're continuing to better characterize this exploration zone concept and for both the subsurface ice-based sites and high-grade mineral sites. So with that, thanks very much. Be happy to chat during break time.